All right, so you're here for the deep dive into chemoinformatics,
That's right.
and you need to know how it all works, like right now.
Absolutely.
We're focusing on the tools and databases that are really like the foundation.
Yeah, the backbone of the whole field.
So this is going to be like your cheat sheet for
Yeah.
the whole digital side of chemistry.
Exactly.
Okay, so let's start with the basics, how we actually see and work with molecules.
Okay.
So we've got software that lets us visualize and edit molecules.
Right.
Things like Pymol, Jmol.
Yeah.
Those let you actually see the molecule in 3D.
Yeah, which is huge for understanding how it actually works.
Right. It's not just some flat image in a textbook.
Exactly.
And then for drawing and editing these structures, you got Avogadro and ChemDraw.
So those are the essential drawing tools.
Yeah, and those move us beyond just, the 2D representations.
Yeah.
And let you really grasp the 3D shape of the molecule.
Which dictates everything about how it interacts and its properties.
Exactly. So then we get into molecular modeling and simulation. Okay.
And this is where we can actually start to predict how a molecule will behave.
Right.
So there's software like Amber and Gromax.
For molecular dynamics.
Yeah, for molecular dynamics. So simulating the movement of molecules. And then you've got quantum chemistry packages like Gaussian.
Right, for looking at the electronic structure.
Yeah, and even tools like VASP for materials simulation.
So this simulation is really a game changer.
Oh, yeah.
Because we can predict so much about how it's going to behave before even having to do extensive experiments.
It saves so much time in the lab.
Yeah, absolutely.
Okay, so now let's talk about drug discovery and the tools for that.
Okay.
So there's docking and virtual screening.
Right.
These tools let us figure out how well a molecule will bind to a protein target.
Yeah, crucial for drug development.
Absolutely. So AutoDock is one that's really popular.
Yeah, good open source option.
Yeah, and then there are commercial tools like Glide and GoldD.
Right, those are widely used in the industry. And this approach, this computational approach, has been so important for accelerating early drug discovery.
Absolutely.
Because you can narrow down the candidates so much faster.
It's about identifying those promising leads early on.
Exactly.
Yeah.
And then we've got chemoinformatics toolkits and libraries.
Okay.
This is like the foundational code for building custom applications.
Right. Providing the building blocks.
Exactly. So RDKit is a big one. It works with Python and C++.
Yeah, very versatile.
And OpenBabel is super important for converting between all the different file formats.
Right, making sure everything can talk to each other.
And this open source flexibility has really given even smaller research groups the power to develop some pretty sophisticated analysis pipelines.
It's democratized the field in a way.
Yeah, for sure. And then, of course, we need to be able to analyze all of this data.
Right, we need the tools for that.
So that's where data analysis tools come in.
Like R and Python.
Exactly. Languages like R and Python.
And all their libraries.
Especially with libraries like scikit-learn pandas.
Yeah, for building predictive models.
And then Kaname is a really cool one because it offers a visual way to design these workflows.
It's a bit more user-friendly for those who prefer a visual approach.
Yeah, and this ability to apply machine learning to chemical data.
It's been revolutionary.
It really has. It's revealing all these patterns and helping us make predictions about things like toxicity and bioactivity.
In ways that just weren't possible before.
Yeah, it's amazing. And then finally, for computational tools, we've got reaction informatics.
Okay.
So this focuses on managing and analyzing reactions.
Right.
And Reaxys and SciFinder are really important resources for this.
Yeah, they're the go-to tools for that.
So those are the main tools. And now let's talk about where all of this information is actually stored.
Okay. The databases.
Right, the chemical databases.
So starting with compound databases.
Yeah, compound databases. So these give you information about structures and properties of different compounds.
Right.
So there's PubChem, which is a free resource from the NIH.
Yeah, a great resource.
And ChemSpider from the Royal Society of Chemistry.
Another good one.
And then ZINC, which focuses on compounds that are useful for virtual screening.
Right.
And ChemBelel, which is from the EMBL-EB and focuses on bioactive molecules.
So these databases are just an incredible resource for researchers.
Oh, yeah. The sheer amount of information there is just mind-blowing.
Yeah, it's a gold mine of chemical knowledge.
And just like we have tools for reactions, we also have databases specifically for reactions.
Right.
Again, Reaxys and SciFinder are key players here.
They're really comprehensive resources.
Yeah, they give you all the context you need about how a reaction works.
Reactants, products, conditions, yields, all of that.
Exactly. And then we have spectroscopic databases.
Okay.
Like the NIST Webbook and SDBS.
Right.
These are so important for identifying compounds based on their spectral signatures.
Yeah, spectroscopy is a fundamental technique in chemistry.
And these databases are like having a spectral library at your fingertips.
Absolutely.
Yeah.
You can quickly identify a compound based on its spectrum.
And we can't forget about protein databases,
Right.
like the Protein Data Bank, or PDB for 3D structures,
Uh-huh.
and Uniprot for sequence and function information.
Right.
These are so important when you're looking at how drugs interact with their targets.
Absolutely. Understanding the protein is just as crucial as understanding the drug.
Yeah, it's all connected. And now, to make all of these tools and databases work together smoothly,
Right.
we need data formats and standards.
Makes sense.
So there's SMILES, which
Mhm.
is a simple way to represent molecules as text,
Right.
and INCHI, which is a unique identifier for chemical substances,
Uh-huh.
and then file formats like MOL and SDF for storing structure and data,
Right.
and XML for more general structured data.
So these standards are really important for making sure that everyone can share data easily.
Yeah, exactly. It's all about interoperability.
It's the language that all these different tools and databases can understand.
Exactly, and that's crucial for collaboration and progress.
For sure.
So looking ahead, what are some of the future directions in the field?
Yeah. Well, one of the big things is cloud computing, making these resources more accessible to everyone.
Right.
And then, of course, AI and machine learning are becoming more and more powerful.
Yeah.
And being able to analyze all this data in new ways.
Absolutely, and there's this big push for fair data principles.
Right. So making data findable, accessible, interoperable, and reusable.
So it's not just about having the data, it's about making sure it can be used.
Exactly.
And then visualization is always improving.
Yeah, finding new and better ways to represent all this complex information.
And I think all of this has the potential to really fundamentally change how we do chemical research.
I agree. It's not just about incremental improvements. It's about entirely new approaches.
So we've covered a lot of ground here, but I think it's clear that these tools and databases are really at the heart of chemoinformatics.
Absolutely.
They allow us to work with this incredibly complex chemical information
Right.
and analyze it in ways that just wouldn't be possible otherwise.
And that leads to a final thought.
Yeah.
With all these advances in AI and machine learning and this emphasis on open science and fair data, how do you think this is going to reshape drug discovery and materials science?
Yes.
Will we move beyond just managing data to actually generating new knowledge?
That's a great question.
Something to think about.
Yeah, for sure.
Thanks for having me.
Thanks for coming on.